Cadence is a resource-oriented programming language that you will use to write smart contracts for the Flow blockchain. A smart contract is simply a program that executes on the blockchain. We can start executing Cadence code using the Cadence language server, a REPL shell, which we used earlier to print hello world. Same command can be used to execute whole files, but on that later. Let's begin by learning about Cadence syntax, and please use the documentation as your reference. So let's launch our interpreter. Here we go. Let's start with a couple of comments. There's two formats for them. Double slashes for one-line comments and /* for multi-line comments. And you can also nest these together. There you go. Same as with most other programming languages, when naming things, you may start with uppercase or lowercase letters, A through Z, or an underscore. Afterwards, you can include numbers too. So here's an example of an identifier that's valid, and here's one that's not. Semicolons are optional, except for when you put two or more declarations on the same line, then you should use semicolons. You declare variables with var and constants with let. When declaring a variable, you have to initialize it. So for example, we have a counter, we initialize it at 10. We can then set the counter to 11 because we create a variable. If, however, we create a constant, in this case name equals Morgan, afterwards we can't set it to something else. We get an error. Everything in Cadence has a type, inferred or explicit, and up to this point counter was inferred to be int and name was inferred to be a string. You can also be explicit. For example, let's declare a Boolean type, an explicit Boolean type, and we can try and set it to true, but we won't be allowed to set it to 42. Cadence has a number of useful types. Let's take a look at some of them, starting with integers. Your regular decimal integers you write out as you're used to in any other language. You can also use the binary formatting, like so. That'll be 15. You can use octals, hexadecimals, and if you're writing out really large numbers, you can use the underscore separator to make it more legible. That's a billion in this case. All of these integers are inferred as int. Ints are arbitrarily large signed integers. If you want, you can be more specific, and you can use something like int 8 or int 16 for a fixed size integer. For example, int 8 can be anywhere between -128 and +127. All integer and unsigned integer types check for overflow and underflow. Here's an example of how that looks. So let's say we have a tiny value that's int 8 and we set it to 126. We can easily increment it by 1 and not have any problems because we have 127, but the upper bound is 127, and if we try again to increment tiny, we get an overflow panic. Incidentally, every panic also crashes our REPL, our Cadence REPL. But yeah, overflow and underflow is built in so that you won't have these problems. Cadence will not allow your integers to be assigned values outside of their range. This protects us as developers from costly overflow mistakes. Integers have a couple of methods. Let's declare an integer to see what those are. All right, so we can convert any integer to a string, and we can look at the bytes that compose this integer. Cadence also has fixed point numbers. fix 64 and ufix 64 to represent fractional values. And these are essentially integers with a scaling factor. And in this case, that scaling factor is 8. Cadence does not have floating point numbers. So let's declare a fractional number. Fix 64, 10.5. Let's see the value. And you can see 8 decimal places in our fractional number. With Cadence, you'll constantly be interacting with accounts, and you can reference them using the address type. Let's declare an example address. This will be my testnet address. These look a lot like hexadecimal integers, so whenever you're declaring variables or constants of addresses, always make sure to typecast them or explicitly set the type to address. And they look like hexadecimal numbers with a 0x prefix. We can take a look at how it prints. Cadence strings are immutable collections of Unicode characters. For example, a name string. Some useful methods and fields on strings. Length just gives out the length of our string. Name.utf8 gives you an array of characters. In this case, we're only using ASCII characters for our string, and we get 6 bytes in our UTF string because it only takes 6 bytes to encode an ASCII string of 6 characters. We can also concatenate our strings because strings are immutable, so the only way to make new strings happen, we can't modify old ones, we have to take 2 and combine them. So in this case we get a third string, whereas our original string stays the same. We can slice up strings. So let's take the first character. It's still a string, but it's a one character long string from our original string, in this case the uppercase M. Optionals in Cadence are used when something can be set to nil or have no value assigned. Let's declare an optional to see how that works. So let's declare an inbox, which is an optional string. Optional is denoted with a question mark after the type, and let's set it to nil as our initial value, or a lack of one. We can then proceed to set that value to something else. Let's say fast forward says hi. All right, and we can set it back to nil. So optionals are very useful when you're not sure if a specific field will have a value set, and it provides you with the safety of being able to check for nil and only read a value if one is present. Cadence arrays are mutable and can have a fixed or variable size. Array elements must share the same type T or be a subtype of T. Here's an example array. Days equals Monday, comma, Tuesday. You declare arrays using these square brackets, and you can fetch items from an array using a zero-based index. But be careful when you're indexing arrays. If you go out of bounds, you will get a panic and you will crash your REPL shell. As you can see, our array index is out of bounds because the size of the array is only 2, and we tried to index 2. Let's go back to our shell and redeclare our array. Arrays have fields and functions, just like other types. We can fetch the length of our array, in this case 2. We can concatenate 2 arrays, So let's say we want an array of Monday through Wednesday. Concatenation, just like with strings, it returns a new array. It does not modify the original one. As you can see, if we want to modify the original array, we can append to it. Appends to the end of the array. So now we'll have Wednesday in our array. We can append more than one element. In this case, we'll use Append All, and that takes in an array of elements. In this case, an array of strings. So let's add, we have Wednesday in there already, so let's add Thursday and Friday. Okay, so now we have an array of length 5 with Monday through Friday. We can remove elements from our array. So let's say we want to remove Monday. We just provide an index and the element will be gone. You can take a look at the array again. Now we do want to have Monday in this array, so let's add it back in. We want to add it to the very front, so we'll use the insert function. We give it an index and a value that we want to insert at that index, and as we can see, Monday's back. We can pop elements from the front or the back of the array using remove first and remove last. Tuesday, Wednesday, Thursday. Cadence dictionaries are mutable, unordered collections of key value pairs. Keys must be hashable and equatable. Incidentally, most of the built-in types conform to these requirements, so you can use them as keys in your dictionaries. An empty dictionary is just curly braces. Let's declare a dictionary of capital cities. Our keys will be country names. Let's do Japan, Tokyo, and France, Paris. Here we go. To index our dictionary, we use a similar syntax as with arrays. So let's see what the capital city of Japan is. Now the return type of a dictionary index is an optional type. So in this case, it'll be an optional string. Now we do have a value in that for that index, for that key. So it's being returned as a string. But if we took a look at the capital city for England, we'll get nil because that's not currently set in our dictionary. We can, however, update our dictionaries and set a capital city for England. And we'll see that we no longer get nil when we query for England. Dictionaries also have fields and functions. Some of the useful ones, get an array of all the keys that are in our dictionary, an array of all the values. We can also check if our dictionary contains a specific key. Let's look at US capitals. And we don't have a value set for it, so the return value is false. And we can also delete elements. So let's remove France. All right. This concludes part 2, where we got introduced to Cadence, its syntax, and some of the basic types like integers and strings and arrays. In part 3, we'll get more in depth with functions and composite types, specifically structures and resources. Let's continue.